This is the first of our standing waves lectures, and today we're starting with waves on a string. So this is like the waves you get when you pluck a guitar string. You actually get this standing wave that vibrates back and forth across the strings, the ends of the strings. So this is like the standing waves that we created with our springs, or we will create with our springs. And when we did it really slow, we noticed that this vibrated back and forth, and these parts were fixed. These parts vibrated back and forth, but the middle didn't move at all, so we shook it a little bit faster, and we found that this part didn't move, and then these parts went from a crest to a trough, crest, trough, crest, trough, and they vibrated back and forth. And then a little bit faster, we got 2 nodes, and we could shake it even faster and get 3 nodes, 4 nodes, etc. This is known, this small one is known as our first harmonic, and it's actually the longest wave that you can get. So it's the longest wave and the lowest frequency. So let's write that down. Longest wave, lowest frequency. And then if we really paid attention to how fast we were shaking it from the first one to the second one, we noticed that we pretty much were shaking it 2 times faster. So the second harmonic is basically twice as frequent as our fundamental. And then our third harmonic with the 3 bumps, see, that's the easy way to figure out which harmonic it is. 1 bump is your fundamental, your first harmonic. 2 bumps, second harmonic. 3 bumps, third harmonic. And your frequency is 3 times the amount. So just generically, the relationship would be to get your nth harmonic, which is like whatever harmonic you're talking about, that would be the harmonic that you're talking about times your fundamental frequency. So if I wanted the 5th harmonic, I would take 5 and I would multiply by whatever my first harmonic was, my fundamental frequency. You can see a demonstration of the actual frequencies and the standing waves at this YouTube location. Unfortunately, it's not a hot link and you can't push on it, but you can write it down on a piece of paper and go to it. This is also a link on Haiku. So how long exactly is our fundamental wavelength? If we take this wave, okay, it's 1 bump, right? And we compare it to a whole wavelength, okay? This is the length of the string. From here to here is the length of the string. And if you see, we're going from this node to this node. This part here is only half of a wavelength. So the length of the string here is half of your wavelength. Remember that upside down Y, the lambda, means wavelength. So in our calculations, we're really going to be using a combination of 3 different ideas. We're going to use that the length of the string is half of our wavelength. We're going to use our wave equation, velocity equals wavelength times frequency. And then we're going to use our harmonic equation, that it's n times the fundamental frequency. Okay, so we're going to use these 3 equations. So now we know what frequency will a 20 centimeter string give off if the speed of the wave on the string is 200 meters per second. Okay, because the wave is traveling up and down the string, not necessarily going at the speed of sound. So we're not going to use the speed of sound for the velocity of the wave here. Okay, so what frequency will it give off? Okay, so the length of our string is half the wavelength, so 20 centimeters is half of our wavelength. So then our wavelength is 40 centimeters. Okay, and we're going to have to convert that to meters, so that's 0.4 meters. So see, we've already answered part of the problem. Check, done. Alright, then we're going to use velocity equals wavelength times frequency. We know that the velocity is 200 meters per second, and that's going to equal our wavelength, which we just calculated, 0.4 times our frequency. So our frequency comes out to 500 hertz. Okay, so that would be our fundamental frequency. Now, if the question asked us what's the second harmonic, we would then take this information and we would say, okay, our second harmonic is 2 times our first harmonic, so our second harmonic is going to be 1,000 hertz, 2 times 500. Our third harmonic would be 3 times 500, or 1,500 hertz. So finding the harmonic itself is actually very, 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 very easy. Now when you're a guitar player or a harpist or something like that, you need to make maybe you want to make your own guitar. And so you need to know how long does your string need to be, or you want to make your own harp, how long does your string need to be to produce 440 hertz. Now we're kind of working backwards. Okay, the 440 hertz is our fundamental, so we don't have to use it. But let's get our equations up. Length of the string is half of our wavelength. The velocity is our wavelength times our frequency. We don't need the harmonic one because we weren't given any of the harmonics. So we don't need this one. So we don't have to worry about that one. But 150 is our velocity. So we're kind of working backwards now because now we want to know how long is the string going to be. We're not looking for the frequency. We know the frequency now. Is equal to the wavelength times our frequency, 440. So now we find our wavelength is equal to 0.34 meters. Okay, so that's the length of the wave. But remember, the length of the string is half of the wavelength. So the length of the string is half of 0.34. Oops, 0.34. Let's get that right. Which is 0.17 meters or 17 centimeters. So if you were to make a part of your harp, your string would have to be 17 centimeters long and it would produce that 440 hertz note. So keep these 3 equations in mind, even though we crossed the one off. Keep the 3 equations in mind. That's going to be what we're using in all of our problems. I'm going to break them down into, okay, what's the wavelength, what's the velocity, except for if you're in honors physics. Now, if you're on honors physics, you have another video to watch because you are actually going to figure out how to figure out that velocity.